Okay, so thank you very much to the organizers for this conference and for the invitation to present here. This is joint work with Stephen Morris. And so let me jump right in with motivate the objects we study with a quote from Keynes. Keynes likened professional investment to newspaper competitions, which were popular at the time, in which each competitor had to pick not the faces that he thought were prettiest, but those which he thought likeliest to catch the fancy of the other competitors, all of whom are looking at the problem from the same point of view. So he goes through the logic of this a little bit, and he says, we have reached the third degree where we devote our intelligences to anticipating what average opinion expects the average opinion to be, and then you can go even higher than that. So what we do in this paper is we take the objects he's informally describing seriously, and we study them in a setting with a lot of linearity built in, but crucially allowing heterogeneous priors in a world where mostly people have studied this stuff before under common priors. It turns out that there's a simple linear algebra of higher order expectations which we exploit to characterize these things and to say things about the beauty contests Keynes had in mind, kind of times social network. So you can do both networks and the thing that Keynes had in mind together. And so what is this paper doing at this conference? Well, I think these higher order expectations that Keynes is talking about are scary and complicated, but linear algebra is simple, so there you have complexity and simplicity. And so, as I said, we were able to generalize and unify results on beauty contests as well as network games via a certain kind of network centrality characterization. And we offer new ways to use Markov chains, which many people here do much better than we do, for a game theoretic application. So that's the overview. Let me jump right into the model. So you have finitely many, everything is finite in this talk at least. You have finitely many agents, and they have uncertainty over two sorts of things. The first thing is an external state, which we call thetas, and think of this as like how much oil is in the ground, some objective external state. And then there are also types which capture what's going on in people's heads. So these are their beliefs about the state and their beliefs about each other. So they may have various information which makes them, let's say, pessimistic or optimistic about the amount of oil in the ground, and further they may have information that makes them that gives them beliefs about each other's beliefs. And all of that so TI is supposed to fully determine all of that. So we have a big overall state space which we call omega, and we're a little schizophrenic as to whether we're interim or ex ante. Much of what I say is true under a purely interim interpretation, but to the extent that we want to talk about some ex ante stuff in priors, we'll say that I has a prior pi I, which is a probability distribution over the entire state space, over the entire big state space omega. So that's the information. So I've told you this tells you everything about the information structure. And then there's also an interaction structure. So we'll introduce weights, gamma. So the weight gamma ij describes how much I cares about j in ways that our applications will make precise, but think of it for now as an abstract weight. So this we'll take the weights to be in a matrix big gamma, and we'll assume that it's row stochastic, the rows sum to 1. And we call this thing the interaction structure. So just as notational convention to alert you to throughout, unless I make a typo, people are in superscripts and indices of states or types are in subscripts. So if you're curious, if you want to know what a letter means. So I've copied some schematic version of this notation here on the left in case you want to refer to it. Yeah?
What are K and N in the subscripts?
So because we'll be doing linear algebra, we'll be interested in indexing these finite sets, but I want to put some order on them. So I've ordered the states theta 1 through the biggest one, and little m is the index. Okay.
How about K?
So ditto for types. So Ti is a finite set of types, and K is the indexes the types.
And those are ordered?
Is there an order? For purposes of writing down matrices, yeah. Assume we picked some arbitrary order on these guys. So just for some, this will be not so useful, but I want to make things very concrete for those who haven't worked with this notation before. So here's an example making all of this concrete. Suppose there's a two-agent interaction. We draw a playing card, and we're going to tell, let's say, Jason whether it's black or red, and we'll tell me whether it's a face card, an ace, or something else. So Jason observes one of two signals, and I observe one of three signals. And in this world, my type is fully determined by what I see. So is Jason. So Jason's type space is just whether he saw black or red, and mine is which of my signals I saw. And theta, the external state, it can be anything you want. If you want the biggest one, you just take the whole, exactly which card was drawn, and then we might play some betting game with that. So that's how you would, encode some practical interaction in this notation. That's not good. Yeah.
You mentioned beliefs on beliefs, but you don't have that here. You didn't have it on the previous slide.
Yeah. So that's a good point. So here I gave you. Yeah. Here I made them pretty trivial because you observe. But suppose I can also peek at your card, but my peek is imperfect, right? And so then I would have not just which of these three I saw, but whether it looked, whether your card looked kind of black or kind of red or something, right? And that would give me, then I would have higher order beliefs too, and non-trivial ones, and they're implicitly all stuffed in here. So if you tell me the prior over everything, right, and then you give me some information, then I can just take a conditional with respect to this thing, and that'll determine my posterior beliefs.
I guess I've gotten confused between pi j and previous slide.
Yep.
I'm confused between pi j and tjk.
So types, you should think of types as just an indexing as many different beliefs over anything as you have. I'll give you a type for each one. So your type fully determines everything going on in your head. So if you want, instead, you can think of this as really a full specification of the whole hierarchy, and I just gave it a number. So, and then, sort of trivially, however I specify it, I can put the prior will contain all the probabilistic relationships between different beliefs you have. Ben?
Does it impose any meaningful restriction on the different beliefs that different types can have to say that they all have to be Bayesian updating from the given prior pi I? Or could I have equivalently written this model and just say each type has a belief?
Yeah, so so I think this will help with Jason's question too. You can define the model fully in interim terms. So just each type, what it literally tells you is a distribution of beliefs over the others types. Where those others types may also have, be so the universal type space is big enough to do this all kind of in one step. And so in principle, you could be working with that if you wanted. But in the example, many practical examples you can write them down more concretely within this kind of black-red framework. So to Ben's question, we can work in a purely interim specification for most of what we say, but it definitely imposes non-trivial restrictions to say they're all consistent with a common prior, and we'll see some of that in the results. Ilya?
The type spaces could be finite, and does it matter because the hierarchies in general could be infinite?
Yeah, so finiteness will, in general, everything I say we strongly believe can be done for compact type spaces, but in full generality, I'm not so sure. So it does impose some constraint. So I'll come back if you're not happy, but thank you for. Okay, so here's the key object that we study. So fix some random variable y. Think of this as the value of the oil in the ground, and let's define two kinds of things. So the first, there's two different sorts of objects being defined on the slide. The first is a first order belief. This is xi1. So 1 stands for first order, and it's i's expectation about y. The letter I here appears in two places. Here, it's because I has private information about the state. And then here, it's because different guys may be using different priors. So I put an I here. If you want to take an ex-ante view, then when you take conditional expectations, I is taking them with respect to a different prior than J. So that's why. So you can't write them as conditional expectations all with respect to one measure, in general. And so it's a first order expectation with respect to I's information. And then once we've defined all these first order beliefs, we can define higher order beliefs. So we can define xi2, here the 2, well, so let me talk about the inside first. So this is 2 stands for second order. And what is this? It's i's belief about an average of stuff. So the average is taken across a population with weights gamma. And what is it that's being averaged? It's various individuals' first order expectations defined in the previous step. So we have all these beliefs about the value of oil in the ground, and then we take someone's belief about an opinion poll of those things.
So the xi's, you said, are random variables?
Yeah.
The xi ones are random variables. The expectation is with respect to which distribution again?
Good. So
The EI expectation? Could you repeat that?
okay, so let's make it very concrete. Suppose the TIs, suppose the y is just a normally distributed random variable, and the TIs are signals just with noise around that thing, right? And so this is, so this is what people think about the random variable given their signals. Then you take this average, and then also given their signals, they can think of this population average.
What I'm asking is what's left random after you take that expectation? That's what I'm trying to...
Well, when you update based on your signal, I don't know what you're thinking in your head. This is all happening statically, right? So I don't know your signal. So I still have to take, if I take, the average of yours and Jason's, there's a lot of randomness there from my perspective.
So TI is a random variable.
That's right.
And this expectation is a random variable.
That's right, exactly. It's a TI, it's measurable with respect to this thing, okay? Yeah.
So sorry for asking something stupid, but that I on top of the expectation. So your belief is something beyond your type. Like your type TI is not fully describing what expectation you're taking. And why are you doing that? Why
So
isn't your type just incorporates that belief? Like,
You could fix it, good.
of keeping that separate.
So we want to write it, if you wanted to write it in purely interim terms, you're right that you would need only one index, right? Your identity and your type fully determines all your beliefs. If you want to take an ex-ante view, then you're taking conditional expectations with respect to some prior measure, and if we don't have common priors, then you have to keep the I around there because they're not the same conditional expectation operator. And I agree, I claim it's valuable for some questions to, okay. So, good. So of course what we've done for 1 and 2, we could do here for n plus 1 and n in general. Question? That's all right.
By the definition, xj should be taken with expectation with j's prior.
It's already in there.
Sorry?
So this xj is a random variable defined like this. So
Yes. But that means that xi, like when I calculate his second order belief, he should know the other people's prior. Is that true?
He knows this?
No, he takes expectation over them with regard to his beliefs.
They're prior according to his belief.
So he understands these random variables. You could think of, so imagine these guys all sit around before they get any information. They know the model. They know that if you see this, you'll think this. If you see this, you'll think this. Now they don't know what you saw, but they do have beliefs about it, and they take expectations with respect to those beliefs.
I think the question was the phi
Yeah.
is unknown to everybody.
That's right.
Okay.
Thank you, Ilya. Okay, so what we'll be particularly concerned about is the limits of these guys. So I define these things inductively, and we're going to study the limit as n goes to infinity. And you may ask, why are you going to study that? So I'll explain, but I want to first give a very concrete example, which may now be superfluous, but I'll quickly go through it. So if we have this interaction structure that's very simple given by a cycle, then typical entries in these iterated average expectations will look like, well, this is a first order belief, right? And then it's 3 pays attention to 1, so then a typical second order belief will be 3's expectation of what 1 is thinking, and then 2's expectation of that, and so forth, and you go around. So if you work with simple gamma matrices, you can think about just sort of regular old iterated expectations of the kinds that have been studied in some game theory papers. But we can think about more complicated ones too if we let gamma be more general. So why would you care about these big X's that I've defined? So here is one reason. There are other reasons too, but I'll give one very, very concrete motivation. Take a simple game this game is a popular metaphor in a few different fields of economics. It's a game where we want to match, there's some random variable y, and we want to match, we're all concerned about matching that thing, but also coordinating with each other. So this is some kind of organizational problem maybe. So beta is a number between 0 and 1, and you allocate some weight to matching. You're unhappy, you receive a squared error loss penalty when you mismatch y, and that gets a certain weight. And then the rest of your payoff has weight beta and comes from wanting to match the other guys. So, and gamma ij describes how much you care about matching with j. And then you get penalized proportional to the square of the distance from him. So the point of the slide is to deduce that in this game, equilibrium actions, actually much weaker notions than, much weaker solution concepts than equilibrium imply this, but we can show that what will be played in equilibrium is this average. So this is an average of these xi's over various n's. So the punchline is that in this simple coordination game, the higher order expectations basically is exactly what's important for how you'll play. And actually, in the limit, we mostly will be focusing on for this game, which is that this term becomes important, that the coordination motive dominates, even though beta is not quite 1, but it's close to 1. It turns out that this is essentially equal to the limit of these xi's as n goes to infinity. So it's really high order iterated expectations that matter for play of this coordination game. So that's why this is one motivation for why we study this, and the rest of the slide gives the calculation for how you establish this. I won't go through it, but it's quite easy. All you do is you write out the best response here, which is basically beta bar is just my shorthand for 1 minus beta. So you put beta bar weight on your best guess of y, and then add to that a linear combination of your best guesses of what these other guys are doing, right? And then you just plug in this best response into here. And if you keep turning this crank, you're going to establish this expression. So nothing exciting there, and I won't show those lines. Okay. So what do we show? So our first result is that these xi's converge as n gets big to a limit that is independent of who you are, so everybody's xi's converge to the same thing. And moreover, it's non-random. All these xi's converge to a constant number, convergent probability, let's say. Pick your favorite notion. So that sort of puts us in business. There's some object to study. And then the rest of what we do is analyzing what this consensus actually looks like. What can we say about it in terms of the information structure and the interaction structure. So first, by looking at the simple complete information benchmark, by looking at the version of this game where everything is known and there's only the interaction structure that's possibly interesting, we can generalize and refine certain characterizations that people have written in the network games literature of what the limit looks like. So that's structural result 1. But then it turns out, so we can fully nest the complete information case, but then it turns out the incomplete information case relates to it in a nice way. And then second, we can generalize a separate literature on iterated expectations under common priors. So there's a well-known paper of Samet that studies that, and it turns out that that's a special case in some sense of our analysis, and we can marry that with networks. So that's sort of the structural picture. And then in terms of new kinds of calculations we can do rather than unifying old results, we show you, once we know what this consensus looks like, we can analyze who matters for determining it. So when you have non-common priors, whose priors matter? And this is the stage at which it's useful to actually think of the prior concretely as an ex ante thing that's really, that's real. So that's the plan.
So the types are also common knowledge?
The structure of the model is common knowledge.
Isn't it, in some sense, Bauman's result that we can't agree to the same?
Which part?
The limits.
So Samet's result is closely related to Aumann's result. It's a different. I mean, I wouldn't say it's exact. Aumann. Yeah, I guess once you're willing, the key thing to see is that highly iterated expectations actually have to be common knowledge. And once you know they're common knowledge, the agreement part follows directly. There was another, yeah?
Yeah, I'm still trying to wrap my head around it, but for this first result, this consensus expectation result, is there any structure that you need on the interaction matrix? I mean, it seems like you could basically be defining two separate games.
So there is a connectedness assumption, and which I'll get. So let's jump into the results, and we'll any other questions before I show you more?
When you say structure, do you mean the gammas? Do you mean more things?
I guess when I mean by structural results, I mean things that hold about the form of this, no matter what the beliefs are. You know, I'm not taking here. I'm going to be taking limits of very particular kinds of games. Those are computations. But structural results are just relationships between.
That's not what I asked.
Oh, sorry.
Sorry. You said that the structure is common knowledge.
Yeah.
And when you said structure is common knowledge, in that sense, you meant the gammas. You meant the.
Yeah, I meant everything that's written here. That players can look at a piece of paper with all this information: the gammas, the full descriptions of the type spaces, the priors. So this is all common knowledge. Okay, so let me do the convergence result formally. Okay. Suppose that there's a condition to worry about your question, which I won't say now fully, but it's called beliefs and interactions are jointly connected. So under a connectedness condition, we can say for any random variable you have in mind, three things. Okay, first, this limit. So this I've already said this informally, but the limit of the xi n as n goes to infinity exists for every agent. And then this limit doesn't depend. There's a reason why I don't have a ci here. It doesn't depend on on who is at the outermost expectation, nor does it depend on the state. It doesn't depend on any of the randomness in the model. So this is the players all know what the model is, but they don't get to see each other's signals, of course, or each other's types as realized. And it turns out that they can compute this knowing just that structure without knowing the realization of the uncertainty. And not only can I tell you this thing exists, but I can tell you pretty concretely what it looks like. Okay? The consensus expectation, and I've copied the formula here, is a weighted average of these guys. What are these guys? These are contingent beliefs. So you might think, so here's what you might be, here's a natural thing to be confused about. I say that it's non-random, but here there's all these conditioning on realized types. So what's going on? Well, no, the key thing is I'm not conditioning on any realizations. Before we get any information, we can sit and I can think, what if Jason were optimistic Jason today? What would he think? What if Jason were pessimistic Jason? I could write all those things, so I know all these numbers. And it turns out that the consensus expectation is a weighted average of all these numbers. Okay? And I'll tell you much more about these weights PIK, which are sort of play the starring role. Yep?
So I'm not getting intuition for this. So let me try to describe a simple example and you'll tell me where I'm wrong.
Okay.
Let's say there is oil or there isn't oil, and there are two players and they get a signal which is fully informative.
Yeah, so this connectedness assumption will rule that kind of thing out. It'll rule out perfect common knowledge, it'll rule out that we play completely disconnected games in terms of interaction, and it'll rule out some other things too. But so your example is exactly the edge case that we need to rule out. Sorry for interrupting, what?
So just the fact that people are getting informative signals, doesn't that already prevent you from having an answer which does not depend on the state?
Well, what's most interesting is that as soon as you move away from your edge cases in even the tiniest way, so assume that I have the slightest uncertainty about what you saw, right? So your example is, suppose that it's a lot of oil or a little oil and it's common knowledge which it is. And then you can't have anything interesting happening. But as long as I have the slightest uncertainty about how much there is, about how much you think there is, okay, then we're immediately, this result now applies. So that's surprising. At least it's not our result actually. It was first observed by Shin and Williamson. But yeah, so that was a helpful edge case to point out. So I lied to you a little bit on this slide. The limit that I wrote there doesn't actually always exist. So everything on this slide remains the same, except I'm going to change this to something that actually, now the theorem is really a theorem. What this thing is a Cesaro sum, basically. So rather than looking at the limit of the xin, I look at the average of them for out in the tail. And when the limit exists, they're the same. And this is defined even when the limit's not defined. So now I've been honest with you. So this is really, but remember, this is what matters for the game, actually. So all our theorems are about this, but when the limit exists, they coincide. Okay, so let me give you a sense of the argument, of what's going on here, and then you'll be able, and then that's really the main sort of technical point I want to leave you with, and then I'll discuss, everything will follow in a pretty easy way once we understand this. So the first, to study these objects, let's go to the linear algebra world. How are we going to do that? Well, why don't we think of this as a random variable, but it's measurable with respect to i's information. So since I has finitely many types, let's just write out all the things it is for each type, right? So you can think of this guy as just a vector with one entry per type of I, recording that guy's conditional expectation. And moreover, we can stack these. Once we have these vectors defined individual by individual, we can stack them up in a big vector, one for me, one for Mohammed, and one part of the vector for me, one for Mohammed, and that makes a big vector that's this big. So the key observation is that the formula defining these iterated average expectations is a linear formula, in fact Markovian, in the previous step. And once we know that, we can write the iteration, the key inductive definition of what we study right here, we can write that guy in matrix notation, and everybody knows how powers of Markov matrices behave. So things are pretty straightforward. And looking ahead a little bit, if we represent the matrix as a network, we can relate high-order beliefs to network properties, and that's really the payoff from doing it this way. So let me make this a little more concrete, since this is a very wordy overview, but where are the symbols? Well, so this vector, the kth entry of this vector, captures what the kth type of I thinks about the random, thinks at stage n+1. And I'll write it, this is just recalling the definition, okay? And now I can write out I can take this conditional expectation and just write it out, foolishly take the undergraduate probability book and write down the form of this conditional expectation. But the key, so you don't need to look at this that much. All you need to observe about it is that it's a linear formula, and you can actually check that all these coefficients sum up to 1 row by row. So this is not fun to look at, but this is okay. I can just write x, the next stage long vector x, as some matrix times the previous stage long vector, and I can describe that matrix to you if we recall the correspondence between matrices and weighted directed graphs where the arrows capture the matrix entries. This matrix is, I've kind of drawn it here. There are, so how many rows are there? Well, there's one for every type of every agent. So here are all of I's types, here are all of J's types. And the arrow from a given type of me to a given type of Jason has weight that's composed of two things. How much I care about Jason as a person, that's gamma ij, and then the subjective belief that this type of me puts on that type of Jason. So that's the matrix B. I've fully described it, and you can check that this is a Markov matrix. So now we care about its asymptotic properties. Well, that's easy, right? We know now that its limit. And so I'm being a little loose here because I am acting like it exists, and there's the usual periodicity worry. But don't worry. If x infinity, so when this is well defined, I can just say x infinity is the limit of this matrix as n goes to infinity, times the initial vector times x1. And from what we know about Markov chains, we know that what this is equal to is a constant vector, every entry of which is the dot product of the stationary distribution of B, the matrix, with the initial vector x1. So but the takeaway from this slide is once we make this transformation, this is all just elementary Markov chains. So we can characterize what this limit is. And the key observation is that now that we know exactly what B is, we know what this matrix is, we know everything that this P can depend on. Okay, since it's the stationary distribution of this matrix, it can only depend on stuff in that matrix. And in particular, it's fully determined by these interaction weights and beliefs about each other's types. So you can think of this as a decoupling result. If I go back to the statement of the theorem, this actually decouples what C depends on into P's, which depend on what I just said, and then the stuff which depends on the actual Y we care about, the random variables. So it decouples the kind of intrinsic uncertainty, beliefs about each other's types, and the external random variable Y. So that's the real value there, because this decomposition could be true in kind of a stupid way. You can always write this if you don't put any constraints on your PI, but now that we know some stuff about what determines PI, this has content. So now let me tell you. So that's now in the last 10 minutes we can actually milk this and get some insight out of it. So let me tell you what I call the structural results. But before that, formal statement of the connectedness condition. Now that I've told you about matrix B, the connectedness condition is just that guy is a strongly connected, is an irreducible matrix or has a strongly connected graph, which is so this condition, I should say, is stronger than either the network or a belief connectedness separately. So you need both. Okay. So let's get some mileage out of this. So let's do a silly special case, but that turns out to be illuminating. Let's suppose there's complete information. So everybody's type is a singleton. So there's nothing interesting going on. It may still be that agents have different beliefs about, so just all the time I have a different belief about oil in the ground than you do. We have different priors. That's allowed, okay? But everything else, and that's known too. Everything is known. So let me remind you of a definition. The eigenvector centrality with respect to the interaction structure gamma is defined as a vector E satisfying this equation. This just says that E is a left eigenvector of gamma with eigenvalue 1 suitably normalized. Your centrality, this is PageRank, your centrality is a weighted sum of other people's centralities weighted by how much they care about you. So if there's no incomplete information, type spaces are singletons, and you can easily see that this B matrix I defined is just the interaction matrix, right? There's no, all the pi stuff is trivial. So in this case, P, this vector of weights, which determines the outcome, is just the eigenvector centrality vector according to the interaction structure. Or in other words, the consensus expectation is a weighted average of individuals' priors weighted by how central they are in the interaction network. So this case is well known. This has been studied in the network games literature. So this is a special case. Now it turns out that something much more interesting is true, which is a big generalization of this. It's always the case, no matter what the information and interaction structure is, that the sum of weights on a person's types is equal to his eigenvector centrality in the network. So Jason has a bunch of types. There's happy Jason, sad Jason, Jason who thinks that I'm happy. And if you sum the weights of all his types, these PIKs, then you get Jason's centrality in the interaction network, which you could have computed without knowing anything about the information structure. So that's sort of the sense in which we refine the standard centrality analysis. In the complete information case, it's your centrality in gamma that matters. In general, your centrality in gamma is shared out among your various types. Okay? So that means that we can write this decomposition where the weight that type K of person I gets is a product of two things. It's the product of his weight as a person, EI, times some number RIK, and by what I've just said, we know these numbers sum to 1. Okay? So these R's generalize the notion of a prior on player I's types. That's a precise statement in the following sense. If there is a common prior over types, that is, if our interim beliefs are consistent with some joint distribution on the whole type space, the product of all our types, if there's some joint distribution that gives rise to all our interim beliefs, then it turns out that these R's just are the prior beliefs on our types according to that common prior. Okay? But this decomposition is valid even when that's not true. It's valid completely generally. And so this R is a kind of substitute. It's a stand-in for a common prior, even when there's no common prior. And if you want to ask me during Q&A, I can give you a more precise version of this stand-in claim. Any questions? Getting lonely up here. Yeah.
So since you made this connection between this and PageRank or eigenvector centrality,
yeah.
There's this notion in PageRank that if you're an individual trying to compute these measures, like if you're I trying to compute the saturated expectation, after some point you might get bored and give up. Mm-hmm. And that leads to this notion of personalized PageRank, because Since you started with your own expectation, you are the starting point, and you can give up after some time.
Yeah.
Is there an equivalent notion? Would that somehow make it computationally easier?
Yeah, well,
That markup is guaranteed to mix, whereas
the getting bored is distributed. You get bored at some random stage of this?
you could define it whichever way you want. You could get bored after 4 steps, you could get bored at every point with 0.1 probability. But so that Markov chain naturally mixes very fast, right? Because you.
Yeah. So let me talk to you more about that. Basically, where we're getting away. So your thing has to do with, I think, the low powers of B, right? Because you take only a few steps, right? And if we look back at like the game, in the game it was an average. So as beta goes up to 1, as you really care about coordinating, I care about coordinating with Jason, but he cares about coordinating with you, and that really takes me far from me. But for low coordination motives, it's only the first few steps that matter. So that's the correspondence. When we really care about coordinating, that gives rise to this distant contagion of stuff. But for low beta, it's the first few powers that matter. Unfortunately, the interesting things I have to say are about the high powers. Okay. So a consequence of this statement that I just made is that if there are common... more questions. Ben?
You may have said this, so I apologize, but in the case where there isn't a common prior, is there any way to back out the individual specific priors from the weights?
From the weights? That's a good question. No, they're in general unrelated. Or if they are related to the weights, it's in a complicated way that we don't know. So there's no natural formula. Alesh? Okay. So a consequence of what I just said is if there are common priors over types, we can get exactly the same formula that we got in the trivial case of complete information. So this I don't know, should surprise you, I think, because the complete information case is super silly, but common priors over types is like what economists study all the time. And so type spaces can be super big, but it turns out that they completely wash out in a sense, right? There's nothing about the structure of private information here. So, and there's an easy proof of this. If we write the general formula for consensus expectation, and then we use our decomposition that we just established, where it's player weight times these R's, and then you use the fact that I just told you that in the common prior case, this is just equal to the prior probability of type K, then you immediately see that this guy inside by the law of iterated expectations is just the prior expectation according to I of the random variable. So you can, and moreover, okay, so there's one more thing you can get out of this. If these guys are actually all the same, if these guys are all the same, because we have common priors over the external stuff as well, then this is just the common prior. So that's essentially, that's a manifestation of Samet's result in our setting, that when there is a common prior about y, then despite all this interesting interaction and updating and whatever, everything washes out. And what we play in the coordination game is just the common prior expectation of y. Strange but true. But it turns out that what's really important is common prior over types, right? If you don't have common prior over types, this result is adjusted in a relatively trivial way. You just weight by individual centralities, but it's about as simple. Again, Eva?
So, say you have almost common prior. Say one of you guys has a different prior, but n minus one of them have a common prior, or something of this form. Can you say anything of how much this C moves away?
I will tell you the best thing I know about that as my last result. Okay. Okay, 5 minutes. So I'm not going to go through all the content of this slide, but basically what we've learned is under common priors, private information washes out in a very, very strong sense. All the structure that I set up ends up kind of not mattering, right? Because the consensus expectation is not non-random, so stuff doesn't depend on realizations. And it doesn't even depend on the information structure. It doesn't depend on any of these details of what people believe about each other. So in general, this second bullet doesn't hold. The consensus begins to depend in an interesting way on the structure of private information. So the rest of the talk is telling you about that. And I think I'm going to, we have an example quickly. So this example, which I won't go through, but it answers Ben and Malesh's question that in general, once you relax common priors over types, you can get very goofy interactions between the network structure and the information structure. And you can't, so basically you can take one network that's a cycle clockwise, another network that's a cycle counterclockwise. The predictions are completely different, even though the model is sort of symmetric in terms of all the priors and everything. So like the individual's priors are symmetric between these cases. So I'll talk to you more about that counterexample or ask me in Q&A. But there is a counterexample showing that stuff can get weird quickly. But I want to, the results where we can do interesting calculations are about whose priors matter. And so that's the last thing I want to tell you about. When you have guys with different priors, you really want to take an ex ante view of the situation. Can we say that it'll be my priors that matter for determining the play of the game? So let me tell you what we know. Remember that in common priors over types, it was the more central guys whose priors mattered. That was the result I just showed. So let's take a quite different setting. Now, no common priors. But let's suppose that we have agents who receive signals. So there's some true state of interest, and agents receive signals about it, which are correct with probability 1 minus epsilon. And otherwise, they have some weird, when you're being lied to, you may be lied to in some kind of interesting way. So a simple case is you get the truth with probability 1 minus epsilon and random noise, uniform otherwise. But you can imagine other structures. We study a structure that game theorists have focused on called common interpretation of signals, which has the following structure. We agree about how signals are distributed given the state. So we all know this, and we all have the same distributions of error in mind, conditional on the state theta. But we may have different priors about theta. So I may be much more optimistic about oil ex ante than you are. But we agree about how our instruments work and stuff. So here's what we can show. Suppose that all these error probabilities are going to 0. So we're converging to the complete information game where our instruments are perfectly precise. But one of them, let's say guy J's epsilon, converges to 0 much slower than the others. So his error rate remains high while the others are relatively low. But all of them are going to 0. Then I claim that it's only guy J's priors that will matter. Okay, so it's the guy so this is a fact about these beauty contest coordination games. Ignorant people win, right? Because if, say, I don't know anything, I always just take my prior action, don't respond to my information in any way, then you know what I'll do, right? So insofar as you care about coordinating with me mostly, you'll just take my, the ignorant one's prior action. And everybody will coordinate on that. It turns out that this is true even when you take these limits, where we're not ignorant anymore. Everybody's quite well informed, but it's still the relatively ignorant guy whose priors determine the play. And so that's the kind of result we can show. And what kind of math is involved in this? Well, remember that to characterize the outcome for any particular environment, we had to study the stationary distribution of this Markov chain B. Now, as we're taking these epsilons to 0, we're studying a sequence of games where the b's are indexed by epsilon. And actually, in the limit, since we're taking the complete information limit, the B becomes what you guys were worried about, the completely disconnected case where we know exactly what's going on. So this B splits up into a bunch of boring components. So to understand, to characterize what the consensus is, we have to analyze the limits of Markov chains that are tending to a disconnected limit, right? So continuity of Markov chains is nice when you're near connected Markov chains, but when you go to disconnected ones, things get goofy. And so it turns out that even to state this result correctly, even to say at what rate, what it means for epsilon I to go much slower, you have to really worry about the structure of the interim beliefs as captured by this matrix B. And for different graph structure of it, there will be, different rates required. So to be very concrete, the structure of the errors is going to determine what rate assumption I need to make, whether I need epsilon j to be big relative to the square of the other guy's epsilons or to the cube or whatever. And I can read that off from the graph structure, and the proofs of this kind of thing go via the Markov chain tree lemma, which we all love. Okay, so this is what I wanted to say. I'll leave this conclusion slide up. I want to say that many people, this is, I put the classic references like Samet and these network games before, but this is a exciting time for us, stressful time, because there are all these smart people publishing papers right now about related things. So I put the ones we knew about. Please tell me about others. And I want to leave you with these punchlines that these consensus expectations are sort of, even though they're defined really simply, there's kind of a lot going on. And they generalize things that people have cared about in other literatures. And for me, the most important thing is that if you have Markov chain intuition from kind of physical the physics way of thinking about Markov chains, you can now start using it to say stuff about higher order beliefs, which are otherwise scary. So, so that's what I want to say. I'm happy to take some questions.
Some quick questions.
Ilya?
So, if I remember correctly, Keynes's quote was application was financial markets. And so your game is maybe somewhat, but not exactly what we think is in the financial market. So of course the result is pretty pessimistic, that there's no information aggregation at all. So is there some way to relate it to financial markets? And is there any information revelation in their game that's more realistic?
That's a great question. We wrote down, just to make the connection explicit, we wrote down a very stylized trading game, which is kind of a hot potato asset. You, with very small probability, eat it, but mostly you sell it off. So in that case, there's no aggregation. But for more realistic dynamic, I think the model is different enough that it's not going to directly say anything about more realistic information aggregation in finance. But Keynes actually thought that the phenomenon he highlighted was going to lead to like volatility and things being very, very sensitive to sunspots and whatever. And so you can think of that. The best thing we have to say in connection to that is because things are deterministic in a component, but they depend very sensitively on the structure of the connectedness structure of the matrix B. So if you think of that changing somehow, if something that was not viewed as plausible suddenly becomes plausible, then you can have big jumps. So that's our. Jason?
In the beginning, you made a distinction between an interim and ex ante interpretation.
Yeah.
And I didn't really appreciate it at the time. I was wondering if you could maybe say a few words now that we've seen all this to
Right.
understand that distinction.
So the matrix B can be defined purely in terms of interim beliefs. It just cares about conditional beliefs on each other's types. But the ex ante things, the places where I use ex ante is so I can say whose priors matter. In the interim world, there's not even such a thing as Jason's prior. So if you're willing to commit and think there is some stage before the game where we have priors over what our signals will be, then we can talk about whose priors matter. So that's the distinction. Ben?
I just wanted to push a little bit on Malesh's question. So suppose I observe behavior in this game and I see everyone's actions, and I'm thinking in this beta close to 1 case, so that people are really playing the consensus expectations. So you said before that you can't back out exactly what the interim beliefs are, but are there any non-trivial restrictions on the interim beliefs? In other words, what can we learn about interim beliefs from behavior?
I see. If you get to observe the consensus, what can you learn about interim beliefs? Yeah. Yeah, so these extremal, right, or you can ask for putting some substantive restrictions on the interim beliefs, what is implied about, what are the falsifiable. So we are thinking about, as you might not be surprised by, Stephen and I are thinking about those extremal questions. They turn out to be hard, but we think there are some characterizations on the convex polytope in which the consensus measure that gives rise to this consensus expectation lies. But I don't have much to say, but I agree with you that it's a super interesting question. I guess I should stop, right?
Yeah, let's take remaining questions offline. Thank you.